Hello, everybody. Uh, oh, okay, good. Mm, so chat here. Can you hear me?
Hi, Jun.
Hi, good. I'm trying to find your guitar. Yes, good. Yes. So thank you for coming, everybody. Thank you, guitars. And now you are the co-host. Please help me maintain the session. Okay, we still have people join. Yes. We can take this a few minutes to address questions. Do you have any questions about the study, the subject? You can speak up, or you can raise your hand, or you can type your questions in the chat box. Uh, okay, give me a sec. I need to switch off my air condition. The screen sharing makes my computer extra hot. Yes. Okay, very well. We are now 5 minutes into the session. Let us start. Okay. Um, yeah. As promised from the last week, I have made a in-session note, which I will share after our study today, which contains the main take-home points I want to make, and you can will try to follow me in the class while we are studying the algorithm and try to program them on a computer. And the most important steps will be shared there in the notebook, which is here. So after the session, you can use this notebook to review the contents, the main contents in this session. Of course, for a more detailed, extended version, you need to go to the Canvas. We need to go to the Canvas to find more online materials. And by the way, of course, I will add new materials there because I remember I promised last week to make some book list. I haven't done, so sorry about that. So you can click the table of contents to have a very quick view of the take-home points for this session. I hope that will help you after the class. Sure. So, but I will build it from scratch. as we work together. I think that will give you some confidence about, okay, the assignment tasks could be done with some ease if I'm familiar enough with the stuff we will learn in class. Okay. So yeah, as usual, let's have a very quick review of what we have done in this subject. I'm bringing my notebook here. Okay. So, well, okay. Yeah. In the first, we introduced what is machine learning, software 2.0, machine program itself. It needs data. We need to believe in some trend, and we do not have explicit representation, so that we need some automatic way to do that. Second, there are 4 elements in our framework: the data itself, some hypotheses set, which is a collection of possibilities. We would like to keep our imagination about this X to Y mapping inside this possibility boundary. Okay, and I have showed using an Excel spreadsheet and put 2 parameters here to mimic the process of selecting from this hypothesis set. Selection, there is a selection method which we call algorithm to select one hypothesis to represent this relationship to be learned, and with respect to some criteria. And in the third and the fourth session, we give an example, our first example about realizing this framework of learning, in which we have studied a linear family of models, well, which assume that, so given the data, for example, in the format table, and each of the columns table, let it to represent a characteristic, an attribute of the data, and we give this a weight and take the weighted sum and arrive a number, and we think this number will comprehensively represent the information in the data we would like to do decision makings, to do predictions or whatever. So this summarization corresponds to our limiting concept of choosing a hypothesis set. This is called linear family. In lecture 4, or of course, in the perception model, we will just do a threshold if it is less than or greater than thing to make decisions. And in lecture 4, we have learned a pictorial, a graphic view of this assumption. Well, we think data as some points in a space, and we represent those points as vectors and think the width also live in the same space as a width vector and the data vector. And this takes the production, takes the sum, is corresponding to takes the inner product of 2 vectors in the space. And therefore, this number will be imagined as coloring the space with using the gradient pointed by the weight vector. And the training this algorithm is corresponding to find a vector that where the gradient when has been set corresponds to the desired boundary between classes. Okay. And in week 5 and week 6 is this week, we consider the second family of model, which is a tree family. In week 5, a tree has been introduced in an extremely simple way that is just a list of if and else judgments. Well, within we have a, if you remember something about, well, where is that? Oh, it's here. Oh, no. Interesting. I'm trying to locate the last. Okay, if you remember something about the notebook we have studied in the last week. Okay, our study lead us to represent this if-else statement into a data format, which allow us to design the automatic selection method, which means to smartly construct and link those nodes into a logical tree-like information flow. So each node here will represent an if-else statement. Well, if-else branch statement, because maybe in some kind of trees you could have more than one, more than two branches at each node. But anyway, for simplicity, we can, to make things simpler, we can stick to the binary branches. Okay, so the if-else statements are mapped to those nodes. We have introduced a structure about those nodes, and we have motivated one of the important design principle of how to automatically do the learning algorithm, which is to measure, well, given the data, okay, this is the guidance which we can use to form this, and the Y part represents the bag of positive, negative labels we want to distinguish. And the guideline is about to make the distinguish of the positive, negative classes as simple as possible. So that is our motivation and our picture of study so far. Okay, so are we good? I'm launching that. While we are letting you think, if you have questions and doubts, please try to ask me. It sometimes is super helpful by just asking questions. Well, by trying to formulate the question in a way that is clearly understood by other person, and you somehow help yourself understand what you do not understand. And in many cases, you will resolve the question by yourself. Wow, that's good. I end the poll now. And I share the result. Okay. As we said before, let's have a look at today's points. So here I didn't number them. 1, 2, 3, 4 maybe. I would call it 3 or 4. Okay. Anyway, so session 6. Um, we will learn to construct the automatic tree building algorithm. Well, second, uh, we will introduce the criteria, a criterion of of making the key operations, do the key operations in the tree building. Criterion for the essential OPs. And the essential OPs refers to answering two questions. One, according to which I split the data. Split. I would not say split the data. I probably uh, a good under a better comprehension would be split. Split the data is what you have you will see in a lot of textbooks, but actually that means which I would like to further investigate the situation or data sample anyway to reach the conclusion. And second, basically this is linked to the first one, just to according to which and well to make a specific decision making, not decision making, uh, uh, a test condition, to make a test condition. That will be clear when we reach there. Okay, so and for the third part, I will talk a little bit about theoretical, because this is a postgraduate subject. I will talk a little bit about the theoretical background of making the criteria, theory behind it. Two parts. One, entropy. Why entropy is defined? So we make a beginning in the last class, but we haven't finished that. Uh, I hope we have some opportunity to discuss a little bit of the details. And two, that will be the relative entropy, um, which defines the criterion. So relative entropy. So this is just a plan. I know there are some unclear points here. Hopefully, we will clarify things during the course. Okay, let's start. So let's have a quick review of what we have arrived in the previous part. Okay, I just copy things here. By the way, hi GitHub. Please keep an eye on the waiting room. When people arrive, let them in. Thank you. Um, and where is our chat board? Is the font size readable on my screen?
Yes.
Okay, thank you. Yeah. So we have started that to make decisions, to make the the information flow, the logical information flow about the if else, we need a data structure, something like that. And the structure works in such a way that mimics. Okay, anyway, that mimics the working of the if and else statement. Okay, so here is the node, and the node knows. I'm always struggling with the windows of Zoom. Where is the annotation window? Okay. Can you see my cursor on the screen? Oh, I need to make it more obvious.
Yeah, we can see it.
Okay. Anyway, the highlight window just disappeared. I don't know. Oh, it's here. Good. Yeah. Thank goodness. Okay. So it knows when it has a decision at this point. So by the fact the information processing flow arrives it, that means we now have a decision about the situation and it can just return decision. Or alternatively, it need to pick up some particular attribute of the data, say for whatever sample arrived, it needs to pick up that value here because that value is belonging to the attribute it is going to test and test against this value to make the further decision where to go. Okay, so it needs an attribute to check, which means here, and then check if this attribute is greater than or less than a threshold. Of course, here is the caveat. In this example, in the class, I'm building a tree that is working on continuous attributes. That means those attributes are numbers. And in the example we have given on the canvas side, we have built an example working on discrete values. Of course, a real tree algorithm can work with both kinds of attributes, and that is an advantage of using decision trees. You can, well, with some effort to mix them in your implementation, and that is highly encouraged. However, just for the purpose of demonstration, because we already have a demonstration working on categorical, which means discrete values, and now I'm building another example working on continuous values. Okay, so it do a test about that attribute. For example, if this column corresponding to this axis, okay, and then it is testing whether that value is on the greater than side or the less than side of this criteria. Okay, so this is the threshold here, threshold of this particular attribute to check. Okay, with this we start. We want to automatically decide, okay, I'm here, given the samples at my hands, should I just return a decision, or should I pick up some attribute to test and decide the value against which the value to which I compare that attribute? That is our task today. I have a question. That is a good question. Before we start building, should we compute the entropy or something? Well, in practical computation, yes, we do that. While when we're building that, you will see in my way, the story is told much easy to understand. Okay, so I'm start building that because of the steps involved. You probably better off not building that in the same notebook with me. Therefore, I didn't use the CodeHawk today. Uh, you can start with a new notebook and try to follow me. Well, for this piece of the code, you can find this piece of code from last week's notebook, which is here in modules and online materials and where is that? There, session 5 notebook. If you click that, it will lead you to the session 5 notebook. Okay, and in the session 5 notebook, you can copy this piece of code. Also, I will copy this piece because that is just to prepare my data, okay, without too much trouble to what okay. I think I just need to hit copy, so I do not repeat this part. Okay, now I have data preparation and I have the basic component of the tree node structure. Okay. I'll give you one minute and then we are good to go. Okay, anyway, I start slowly. You will be able to catch up. I do that really slow right now for a few minutes. Okay. I'm doing a function that accepts a node, some data sample. Okay, and I will build things on the node. Build things, build stuff for node. Basically, I will, depending on especially why, we will give values to node dot decision node dot attribute to check and node dot threshold if we do check it, and the children. After checking that, we will split the task into subtasks. We need to give the subtasks to the to dedicate them to children. Okay. Hopefully everybody is ready now. Okay, now we restart, and here we have laying out our plan. We go according to this. Sure, let's do this. So let's check if our data is ready. Okay, it's good. Well, this is a typical input into this. Okay. Remember our first decision of, well, the decision, you need to distinguish in the context what decision means. Okay, now I'm meaning a meta decision about the algorithm, not a decision about this particular sample. Okay, so the first decision is to whether to return a decision, like if self.decision is available. And now we will decide, given this group of attribute, this group of data. So maybe this is the plus, negative plus samples associated with the data, the y part. Given that, should we have a decision at all? This is very intuitive. Well, if it happens that we do not have any data at all, for example, by cutting somewhere for some part of the card, we end up with an empty thing, or for some example, maybe the corruption of data or something. Anyway, we need to defend against this ill-defined situation. So we would say if the length of y is 0, then not self. We can give it anything just here to make it valid, therefore to stop the processing further. We can give it a value, or maybe we can just give it a positive value at different, maybe in real project, you have decisions to make. Some decisions is riskier and some decisions is safer. Like if the data is a sensory data, the temperature, the particle detector, stuff like that. And the decision is to whether or not to trigger a fire alarm. And in this case, when things arrived in an uncertain situation, maybe an alarm, a trigger an alarm is a safer decision. So you can choose some default decision here. Oh, I just put a default decision here. There's no reason, I just choose that for the default one. Okay. Well, actually, I can do better, because in the next step, I will consider another situation when the decision is made. Consider that if, for example, my samples are not this many, are only those highlighted ones, positive one, then basically I have achieved consensus in this particular area of the data space, which means I'm arriving at a coherent, a smooth, homogeneous part of the distribution of y on the domain of x. When I find myself in this domain, I would happy to just return a consensus decision. Okay. So putting these two parts together, what I'm going to do is I will take the unique value of the data, and I would like to return I would like to check if I have 0 or 1 unique y values. By unique, I will show you right now. Now look, this is not unique. You have 2 values. You do not have a consensus, right? So when this achieved only 1 or 0 values, that means either we are lack of data or we have arrived at the area that all data agrees. So sorry, this numpy dot means from the library of numpy. Okay. We can do this. Else if then that means in this array, when that array contains only one element, we return that element. Of course, now the U has 2 elements, but I just to say this will return the label of the Y. And of course, do not forget stop further building. Here, actually, you can forgo this, delete that, and put everything inside this course. That will be okay. But I just personally find this is more assuring to look at. So yeah, let's go ahead. And now we have arrived at the true stuff, which the true challenge, at which we have different classes to distinguish. Okay, we will loop. We will explicitly check which attribute of X we will, against which we will do the split. Okay, we do a for loop first. Attribute number is X dot shape. What is that? Simple X dot 75 and 2 attributes, and the second element of the shape 2. So we loop over this. Okay. Now to make things easier, I will just take xi x. So this is just to save some typing. Well, and then we want to now look well. The check means we are trying to copy, not trying to copy, we're trying to see if we split against xi, what we would. inquire about y. Okay. So we try one by one. We haven't decided yet. Keep that in mind. We haven't decided. Okay. We try this one. Okay, and we try some values. I just give the value arbitrary, not very arbitrary, but this is a silly way. You can of course do things much better than me, but I just give some trial. Okay, I will do the v0 to be the maximum value of sorry, minimum value. 1 to be maximum value of attribute. Wow, the range, and I will try values to try. Maybe that is 0.25 times v0 plus 75. So it's closer to the small n. Okay, and second one, let it to be half. And the third one, well, I would make it, sorry. Okay, basically, that is to see v0, v1. We pick up 3 values here, here, here. Okay. We test it. Okay. Well, now we will test what would we gain if we split the data samples, the bag in the bag of the data samples according to some criteria, we split it into 2, and how much we will gain in terms of the certainty about the y value if we split it. Okay. I would write a function, see maybe how much we have made progress, measure progress about the decision of y, measure progress. Well, we test measure progress about making decisions of y by taking test xi against thresholding at value xv. Okay, name that as a gain. Then we do some bookkeeping stuff. If best gain, and we of course need to initialize best gain. Okay. So we keep that, and that best I to be the I here, the attribute here, and well, what is that? Value test. Just a stick, okay. So this, look at this part. This corresponds to the end of this for loop. Now, okay, we will test that. To do so, let's split. Let's split the value according to this. So what we will do is to allocate. I do that simply. I'll allocate two index variables. Okay, it is like here. I'm testing here. I'm testing here. So what I'm doing is greater than index will be this x best I greater than and less than okay. Now we have the two groups of data and we will allocate two new nodes greater than and allocate the data to them, right? So what we will do, so we create two new tree nodes, okay, and we will call this to that it not self. This is node. I will explain this later. This is some technical issue, and that will be this the x where the attribute test is greater than the value of the criterion x. Okay, I show you example here. See, if I write from index to be simple x chain, I will let is maybe the second attribute is greater than, for example, 5. If I take this as the index, and I will use this index to index the data table here. And what will I will have? Well, okay, we do not have such samples. I choose a different value to test, maybe. Okay, and you can see for all the samples, we will have this second column greater than 3. And we can set up the criteria a little bit different, maybe 4.2 that will filter out most of the samples, and we can see the effect. Uh-oh, maybe 4. Maybe the 4.2 happens to be the largest value. Look. Okay. So a binary condition can be used to index arrays. Okay. Similarly, we created this here, and that would be less than and less than. I think basically we are done, right? I'm copying some code to test the copy. Okay, I copied the visualization part here, and let's run that. So this is the realization, and let's do the given. What we will have, of course, an error. I'll show you shortly. Um, okay. Error. What error? We haven't actually defined the measure progress. That is the core part. That is the second part we will study today. This is the core part. Okay. We need to address this. But for now, let's just do a dummy one and see how the framework works. Okay. Let's do a maybe very uninteresting implementation. So let's measure progress to be a lambda function. Lambda function is a simple way to define function. You define the input, 3 inputs, and only the number is important. You can call them A, B, C. Okay. And I just return a random number. So basically, this is a super uninteresting placeholder. Okay. Well, I haven't set up. Sorry about that. I forgot to put the node in this part. I have put that in the comment, but I didn't write it down. Best I. This is something to test. Node dot each threshold to be best value. Hopefully this time it works. What? Let's look. By the way, because I was typing all the way, sometimes I miss something. If you find I missed something, let me know. And we have a quick check.
What's the meaning of the fit function in the
Which?
in the line 44 and 45? Fit function.
The same one here. It.
Oh, right.
Oh,
Yeah.
yeah, but now it will dedicate the task to its children. So that is the purpose. Okay, I think let's put it somewhere up here. Okay, and okay, let's go. Oh, that is a little bit interesting. I'm doing some debug here. So it is the first one. Okay. Basically, that means the first one has arrived there. It should have it shouldn't arrive there because it's hmm? Oh, it's my fault. I need to I think it's oh, I haven't done the feed part. Okay, that is a little bit silly. Sorry about that. We have done all the work, but haven't called that. Sometimes that happens. Yeah. And I remove this debug print. Okay, go, and we will see some not so interesting thing. But amazingly, it works. It works. Look, it somehow cut the data space into different regions, which looks well perfectly differentiate the different kind of not very perfect, but somehow to differentiate the different kind of samples. But there's only one thing is this cut obviously not very optimal. This is basically randomly select a hypothesis that happens to agree with the data. Well, that is not according to our principle. Our principle is to find the optimal cut in each step. How to do that? Well, as we have discussed, for the first step, we need to be able to measure the information inside the the Y part. Okay. So let's now concentrate on the measure progress part. We will implement that. And hopefully, I think I'm addressing a question before. Here I'm going to measure the information, and we emphasize again, this could be done in different ways by just measure how pure the Y is. But I choose to use information measure. It's principled and it is used ubiquitously in other research of machine learning. So it is really cool and interesting and useful to learn. Let's do that. So we want to measure the information contributed from X to Y. Before do that, a reasonable approach is look. I'm mirroring in the back. So here is some creature. Here is some creature. Here is a creature like this. I looking like I am doing some anti uh, bacterial drugs, whatever. So this is a bad guy. This is a neutral guy. Okay, I can forgive it. This is a bad guy. Maybe this is also a neutral guy. So I'm designing criteria, and the 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 way of thinking is I try to test which attribute of these creatures I'm going to test to distinguish. After testing that, I will have two bags. In this bag, I have only maybe as pure as positive bad guys, and these are the neutral or guys on which my drug could be more forgiving. And a natural step to here ahead is first, I'd like a measurement about how pure of these symbols, those plus and negative itself, without looking at the x part, right? So that is the definition of entropy we introduced before, and I implement that here. The definition of entropy is like that. If you have some classes, well, class A, class B, class C, class D, and of course, in our case, we only have class positive and class negative. Okay, so you have a frequency of happening of those incidences. We want to measure how uncertainty exists. Okay, and consider that as probability A, probability B, probability C, probability D, and this is probability negative, probability positive. I'm explicitly writing this down to list your confusion when we write an equation like that. This I, this subscript loops over distinguished, distinctive, well, occurring distinctive events in the two bags, in the bags which we are interested in. Okay, keep that in mind. So we are writing the code. Now we do not need X, we only need Y. Okay. And only the distinctive values of Y is important. So S0. Okay. We consider that. And what's more, we would also need to count the numbers of different distinctive values. Fortunately, NumPy just give us this for free. So let's try to do this. If you just do this, oh, okay, this the original Y has 3 classes, and we have a simple Y has only 2 classes. And we can add an option. Look, it is really convenient. Return, okay, return counts. What?
You wrongly spelled the truth.
Yeah. This is typo. Now look, we do not only have the numbers, we also do not have the values. We also have the number of samples that taking these values, which is really helpful. Actually, this is not used at all. Remember in the definition of the entropy, so what I is insignificant. We do not need that. Okay, I could looping over, well, people, events, whatsoever you name it. Okay, and now we compute the frequencies. I remind us that we remind us that This is not a probability. This is observed empirical samples from the probability. It could be completely possible. Some events have a really rare possibility to occur, but it happened to give you more samples at this time. That is a really a possibility. And that is why machine learning is a stochastic business. Okay. Okay, let's just compute the frequency. And take the logarithm of that. I could stop here, but I sometimes, because this is a log function, it would be good idea to give it some numerical safety. Okay, just like that. And do not forget, we need to take 1 over that. Okay. This will be this part for each event. And that will take the element-wise product with the frequency of. Okay. And we then take the sum of this and return that. Done. Let's test that. Should be simple way. What? Hmm? I must have done something wrong. That's bit embarrassing. Hmm? That's wrong. That's completely wrong. That cannot be the piece. Oh. Hmm? I may damage the simple y somehow. Yeah. Oh, okay. Sorry. Forgot this. I demonstrate to you, and then I thought I have implement that in my code. No, I didn't. So, well, that happens when you try to live demonstrate coding. Happens always. Okay, so look, that is for a situation that is really uncertain, 50% of the chance. When I try to communicate one outcome of this experiment, I will spend 1 bit for the communication. There's no saving here. Okay. Then how about let us do some split according to some criteria. We didn't do stuff here. We just hand pick something to test. Okay, how about here? Let's do this. So um, this is greater than 5.5, maybe. So this is just to take the number of this group. We can do this later. Doesn't matter. I will take the subgroup of this, maybe subgroup of that. Okay. Remember, I'm selecting the rows in the data table which meet the selection criteria set up here. Okay. Well, let's see the subgroup. In the subgroup, what is the entropy of the Y? I think I need to disable the buffer. And let's go. So look, in this subgroup, it's significantly less than the entire group. Note that this is not related to that the fact that the number of samples is smaller in the subgroup. No, it's not like that. It is because the distribution of the Y is more skewed in the subgroup. We can see. So look, in that subgroup is more likely to take one class than the other. Correspondingly, you can do for the other subgroup. In that sense, okay. And you can take the weighted sum of the two groups. Okay. I make things maybe a bit slower, but more obvious. So this are just to take the number of samples in two groups over the total number. Therefore, we take the weight. Okay, weight greater than times h greater than plus weight less than times entropy of less than group. So let's go. Say in one group, the entropy is this. Sorry, this is in the other group, the entropy is this, and the weighted sum is this. So the weighted sum is less than the original entropy. Okay, so let's take this as something. Receiving of entropy is h minus h. So we have received 0.5 bits of encoding y, given we have tested against some x. Oh well, congratulations if you follow along. Now we have already introduced the second part of the computation, that is the conditional entropy. The entropy of a random variable given the knowledge of another one. Okay, that would be the knowledge of y given the knowledge of some x, some attribute of x. Okay, you can remember. Uh, you can remember. I don't know how to call that, illustration or something. If this represents the information in variable x, okay, and this represents the information of variable y, okay. So this will represent um, the code cost to, sorry, the cost code. So sorry, let's do it this way. Yeah. Given x. This entropy, this is entropy of y, and this is entropy of y given x. And that is just as what we have done. Is defined as the definition of the so that means greater than or less than, because by testing x against a threshold, we have convert that x into a binary variable as well. This is basically, instead of directly compute that with respect to the attribute, we compute that with respect to the result of the test of the attribute by comparing it with the threshold. Okay, so this there are two conditions, two possibilities, greater than or less than this I. And in each of the condition, we compute P that is within this situation the corresponding Y. This is called conditional entropy. And this is called relative entropy. That is given the knowledge of X. What is left? Well, what is left to of the knowledge of Y? You can check after the class to think, oh, what about if X and Y are unrelated at all? X does not contain any information of Y. In that case, you will find this does not work. The xi, given xi, yj will be exactly as yj itself. In that case, you will find there's no ceiling here. And on the other hand, if xi deterministically, which means it determines decide y, given xi, there is only one possibility of y left. There is a certain relationship, then every summation here will result in 0, and we will find there's nothing left to code, and these two things will completely overlap. Okay. And yeah, so I think that is what we are going to introduce here. And for the coding, I will copy another piece of code which basically implements the same thing, but in a more systematical way to wrap that in a function. I will not take much time to do that. We can just see the result. Okay. I copy my previous implementation here to list the chance of bugs or things. Yeah. So you can see basically what I'm doing here is exactly what I'm doing here without too much printing stuff like that. And look, now I have a new mirror progress. Okay, I just defined that. Okay, let's go back. Now we have a new mirror progress, and I will remove this fake one. Let's go again. Look what we have. It's like a proper building of the classification boundary. Okay, so you can use this example, go back and study your own decision tree implementation and use that for assignment 2 as well. Okay. I think we have go very far. Let's see if you have any questions. Are we okay now? If you have questions, just speak up. From my point of view, here we are very successful. We have many people follow along. And I remember remember that I have reviewed the early student feedback from last week. In this class, people asked me to do more demonstration and assistance in the software implementation, so make the introduction mixed. If you are happy with this, let me know. If you think maybe the coding is too difficult, or you need more help, let me know as well. Or you think this is too simple, with better to address more theoretical part, you can also let me know. Okay. Thank you for the feedback anyway. Okay. That's good. Sure. So if you are fascinated about the information theory, here is a great book about it. It's called I well the camera makes this thing flipped to myself. It's called Information Theory, Elements of Information Theory. Okay, and I will recommend this book about information theory. Anyway, it's amazing, isn't that? You can have a book this thick just for the elementary level of introduction of measuring how uncertainty a thing can be.
Hi, June.
Yeah.
Yeah, about the coding, there's a variable called value to test. I don't understand what is that.
Can you specify the cell and the line number?
It's
So
under the fit function. Yeah, for SV in value to test, it's just a few lines above that.
this?
The one above that. If you move, right, yeah, line 27.
Okay, I here when we select one attribute to test, then we decide the range of this particular variable value,
Yep.
and in the range we select some possible positions to cut. You can make that more cut it finer or cut it coarser. Let's try in a very brutal way. See, in this case we can only cut halfway, okay, and see how the algorithm behave. And now note that for whatever attribute, it can only cut halfway. No other values are allowed. Okay. Let's see.
Okay. Yeah.
So the first cut happens to be here, or maybe the first cut happens to be here, and then here, and then here, and maybe you can see that it's always cut halfway of some attribute, right?
Yeah.
And you can make them finer. See, let me do that. This don't blame me for the black magic. A times V0 plus 1 minus, okay, maybe 1 minus A times V0 plus A times V1 for A in NumPy dot A range. 0.1 to 0.91 with a step size of 0.1. Okay. I won't explain that. It's basically it will generate a cutoff here, 10 cuts. Okay, and if we do this, now look, actually the boundary looks simpler, but why? It's because now the algorithm has a freedom of choosing some better places to put the cut, and then after one cut, the situation becomes more distinctive for Y. So if you investigate this location, it has more freedom along this line, and this location it has more freedom along this line.
Okay. And so how do we decide on where to cut this range of data?
We didn't decide. We check each one of them. We decide the choices, and then we look over all the choices, and then we test if we cut this attribute at this choice. What is
Uh,
the gain?
yeah, yeah.
Okay.
Got it. Okay.
Yeah.
Right. Thank you.
Okay. So that's good. Um, well, let's go to the quiz first, and if we have more time, I will try to address a little bit theoretical behind that. It's really an elegant theory, and if we do not have time, I give you I think you can find in the library from this for this, and for the extraction of the book, you could find from the internet. For the introduction to the conditional entropy, and you have the look, you have the theoretical guarantee that you will always save the coding by looking at the the information of one X attribute. By looking at the information of X attribute, the situation of Y will always become clearer or equal to the previous one, um, according to our measurement of information. That is a really a well-defined situation. You the definition won't allow you look at something and then you get more confused about um, the Y variable. That is guaranteed. There's a theoretical proof of that. The worst situation is X does not contain any useful information and there is no improvement. And that's all. So that is this piece of knowledge um, is discussed in chapter 2.0, sorry, 2.6 in the book, and you could try to Google chapter 2 of this book. And for the definition of entropy, that is given in the Asian paper. It's called, well, I read it, a mathematical theory of communication done by Shannon. And the entropy here, we usually call that Shannon entropy, is from here. So the principle behind the definition of entropy is given in the appendix of the paper. Although the paper is really ancient, old days, but it's very well written. It's like very inviting to read. The reading of that is purely enjoyable. Intellectual adventure is in the appendix 2 of the paper. If you are appendix 2 of the paper, if you are interested in, you can look at into this paper and have a more deeper understanding of that. Okay, if we have some time, I talk about that. If we do not, it's okay. You can look at the references and you can ask me questions in the next session. Our quizzes. This is here. Oh, I haven't published that. Here, I apologize for that. Okay, I have published that. I set up the availability of the quiz, but I did not realize it hasn't been published. Okay, let's go through that. Now you have access to the quiz. So as usual, the answers, the wrong answers are informative. It reminds us some misunderstanding of the concept. Let's look into that. For question 1, okay. The correct answer is that one with a big never, as we have just discussed. So it is guaranteed the entropy of the target computed on the subset of training samples of children nodes can never exceed that computed on the parent node. That is guaranteed. And look at the other two wrong answers. So question one, sorry, the first one, the ID3 algorithm will return a tree of least number of questions. Well, although that is the design principle at each step, we want to gain as much information as possible, but that is a greedy algorithm. By greedy, we mean it looks only one step at a time. It does not have a global view like, okay, I have a perspective, maybe I can sacrifice some gain at the current step for the future much optimal, well, outcoming. For example, if I can save my inquiry of the question one, instead I choose a less informative question two, but I know that after I have asked question two, then I could ask another question three, and two and three combined together will give me a much better clarification of the situation than if I first ask question one, then choose greedily other questions. It does not have this planning. In each of the steps, it's just to choose the best question to ask is here. Okay. Whenever the best gain is exceeded, it will take the new question. The well, anyway, you know that the apparently best question to ask. So the second one is easy. I want to read all the text. You can do that later, but the key point is the test. As we have said, everything has been computed upon the subpopulation, and the population is computed in the population that has been sampled from the data distribution, which may or may not reflect the true frequency. Okay. Question number two. When there is no conflict in the training data, decision tree can achieve zero error. Yes, that is true. By copying more and more and more and more times, eventually you will be able to perfectly split the data. Okay, question number three. That is an interesting one. That is related to the definition of entropy. Here, the up a bit here is. This refers to the intuition that this part we consider if an event has the probability of P to occur, then that event will need this many bits to encode. For example, if P is 1/8, okay, where we need some synchronization, okay, and Okay. And right, and that is to see nothing more than if I have this many, I need to specify one guy from this. I would need at least use a descriptor, a binary descriptor of 3 bits. Okay, I can use the first bit to distinguish these two. Okay, I can use the second bit to distinguish the, the splitted situation in the two. I can use the third bit for this. Okay, and therefore you have this guy 0, 0, 0. This guy 0, 0, 1. This guy 0, 1, 0, 0, 1, 1. Basically, that is how a binary a number is made, right? Okay, if instead of this, if p is 1 over 32, how many bits do we need? Right, 5. And the question asks, if we have a new technology, we can distinguish things not in 0, 1. However, we can have C, A, B, C, D, E, F, G, H. 8 different days. So our code would be something like A, H, C, D, G, things like that. Then if we use this to encode, of course we can have a shorter code. How much shorter? Okay. In this situation, we can use just 1 bit. Yeah, because we can split things in 8 ways. And by adding another 1 bit, we can split 64 situations. Another bit, we can split 256 situations. And therefore, our code length will be 1/3 of the binary code. So this will be this. Let's submit. Oh dear, what happened? I think I misclicked thing. What I said was correct, but I misclicked this answer. Okay, should I? What we have discussed is correct. Don't be misled by this. Okay, and yes, and 1/3. Okay, so How does that going? Is that good? Oh, we have two people need help. Then you can speak up. So can you show the misclicked question again? Okay. The correct answer should be, and the entropy of the target computed on the subset of the training samples children can never exceed that computed of the parent code. That is what we have talked that this part. By checking the knowledge of X, you will always see something to encode Y, or maybe this should be here. This is the sieving. Well, if X and Y are completely unrelated, you would have two detached circles, and there is no sieving, but there is no waste either. Do not try to see, okay, the third answer, because the order of the answer is different from my screen and on your side. They are shuffled. Okay. So maybe you can use the rest of the time to let you ask questions. We have 10 minutes left. I can rush you through the information theory part, but I don't think that is very helpful to many people. Uh, if you are interested in, you can ask me in the following hour. I'm still here for another hour. You can ask me questions, or you can type the questions in the chat box. Well, if oh, of course, let's do a quick review for today. There is where is my session 6? Okay, so I will share the link to this notebook after the class. You can click the table of contents, and it summarizes the take-home points for today. Well, basically we discussed with programming the construction of decision tree building algorithm. And the decision tree data structure gives us the capability of just build and link these nodes to effectively implement a theories of if and else statement. Okay, well, and we discussed the structure of the fit function. Oh, sure, I have to note that this is implemented as a demonstration. You can implement the fit inside this template of object class. Well, put the fit in the function here and give it a self rather than a third party well argument. But anyway, that is a technical issue, doesn't matter too much. So the fit function first decide whether the decision could be made at this step. If it could be, it makes decision and stop the building. This means that reach the leaf node of the tree. If it's not at the leaf node of the tree, we will look over the attribute of the tree and we will try to test to split the data against by checking at some attribute and by cutting it at some value gets the subpopulations. And we measure how much information we can gain from this split. After we have decided the best attribute split, we will build the sub trees from here and call the fit function recursively. So this is the recursive building algorithm. So note that in the demonstrated implementation, I have another parameter that keep track of the depth of the tree, so that you have the option of early stop even without reach the consensus. Maybe you find now I have reached the over complex tree. I can just stop here, tolerate some of the trimming errors. So we then consider to measure the information gain. And to measure information gain, this is an example of measuring the entropy. We measure the entropy of a population of Y variable, and then we manually split the population of the data according to X. We split according to X, and then we measure the information gain on Y. And with this, we see how much knowledge we can gain of Y from the X. And that is the measurement. We take this, we compute this measurement for every X attribute and test that for every possible cutting point. And then we select the best one to construct the tree. Okay. So basically that is what we are going to discuss today. Okay, I wish you have a good evening. So if you have still have more questions, or you just want to stay here to listen to more discussion, you can do so. But before that, let all of us have maybe 3 minutes break, and I will then stay here for another while to address questions. Okay. So if you want to leave, thank you for being with us. Bye bye. Okay. Yeah, you can ask me any questions if you like.
Hi, June.
Yeah.
I want to ask you a question about assignment 2.
Yeah.
So, if I build a decision tree model, does it have to work on both numeric and categorical attributes,
No,
or it can be either numeric or categorical?
it can be either. Yeah.
Either.
Yeah.
Okay.
Mhm.
All right, thank you.
Well, but the different the distinction is not mm, that difficult to address. If you successfully build a framework of that, you probably just need I think two 1-2 hours of actual work to make it work on both way.
Mm, I don't know how to how to code like that yet, but I have to look into that. Do you have any recommendation where can I find some resources like how to implement both categorical and numerical?
I didn't check that specifically. Uh, well, but that isn't that difficult to test. I let it's a pretty it is a bit straightforward extension from where we are doing here. We can either extend here to accompany the categorical values. Alternatively, we can extend from what is on the canvas side to accommodate the, the numerical values. Let's try here. Well, let me see. Here we go. So how to do like numpy um, is oh, I remember that. I think uh, yeah. So the given the given the value of y, now you can sorry, not y, the value of xi. Now you can determine whether what is the data type of xi. Um, let's just do that. Xi for x. Any example. Look, that is a numerical value. So maybe we check um, I see now. Value. Okay, identify. Uh, so, well, that is interesting. Look, that is some details, a little bit hairy. That does not contain a particular attribute that's telling you that, okay, this type is numerical, this type is discrete. You need to somehow distinguish them by yourself. So we can just maybe make distinguish by ourselves. Mm, Subclass. No, it's not this way. Okay, it's the technical issue is not that. Oh, sorry, it's my fault. It's my fault. You should not do this. Um, try to do. We should try to first determine the class of the type. Can we do this? No. Okay. Uh, this subclass. No. Even okay, double type. It's not the type. We can try to. We take one sample. Okay, now this works. This is a continuous value. Mm, int? No. So, well, sorry for the googling and the confusion. Basically, here I want to determine whether it is categorical or a numerical. Once we have decided that, um, the rest part is easier. So let's see. We branch from here. So if numerical. So So the first element of that attribute is a float number. We move that this way. That could be integer, or it can be a string, I think. Okay, then we do not need to do this stuff. We can do X unique. Okay, non-public. Right? I think I'd better to okay, because this is also related to the numerical thing. We'd better to do the uh, split part here. We also keep we can also keep a record here. So best type numerical, and we in this way we would do something here. Best split type to be categorical here, and this we won't change. So and no, okay, there. Right. Okay. If this is numerical, we do the same thing. If categorical, we then do that later. Okay, so measure progress. We create another function to dealing with those this categorical cut. So okay. No, we do not need to loop anyway. We can just write down the cut right here. What to be do? What is to be done is here. So this there is no need to test different cut locations because look, to cut different locations is a way of converting the continuous value into the the binary values. It is cut here, so this is less than, this is greater than. Cut here, another way of assigning the less than and the greater than. But now it is a categorical one. It already has uh, all the categorization done. So let me put here. And I would see that, right? Yeah. So fantastic. We need to implement this one, but before implement that one, we can finish doing this, which is just to see. Let's see. Right? And for each value here, we create a branch. It is like now not only two ways, but multiple ways according to the unique values in this column. And we create a node value here. Okay, so subgroup index is the samples that happen to take this value. You can use a bracket to make the priority more explicit. Well, then we can fit more. This is the one we just created. That one using see. Let me have a look. Okay. Okay, done. So that is the implementation that includes both both uh, both types of nodes. Of
Yeah.
course, yeah, we need to deal with a situation like what happens sometimes when the logical flow happens to hit here. We need maybe some safeguard. Stuff like that. I won't do too many stuff like that. Well, then the next step is to implement this essential piece of what the categorical, where is it? this categorical way of measuring things. Okay, we'll put it in the same cell. Okay, this is the same. We need the entropy of the Y itself. Okay, and then we need to look over all possible X values, right? This is the same here. The structure is shared between them. So I and this, and we mm, so this is the index. We need to take the sum of the subgroup, and we compute the entropy of the subgroup. Then that's it. Entropy of the subgroup. Okay. We first find the subgroup of each individual, each unique value of the X, and for the subgroup, for each of the individual value, we take the subgroup, and then we compute the weight of the subgroup, how much portion of the population it takes. Then we use this weight to compute this term. This is the weight, and this is the subpopulation, the entropy of the subpopulation. Okay, and so entropy, which, well, we take the conditional entropy from the entropy. Okay, and one more thing. Here we get the best split type. We need to, okay, it's here. So we need to change the definition of the tree node to accommodate this capability. Okay, and now let's look. If numerical, we then go in this way. Otherwise, we go for the categorical one, which is what we have done on the camera side. So we change and just take this value. Okay. Actually, here we should take some caution. For example, I write it down. So this is a formatted string. This is a formatted string. Okay, done. So probably that will contain some errors, but basically that is how you deal with both types um, of attributes. Well, I think this is maybe more than you have asked, but
That's
I
great.
try to try.
Yeah, that's awesome. Thank you so much. Thank you.
Hi, June.
Yeah.
Hi, I have a question. So I'm not very good at coding in the beginning. Like I don't really have much background. So I feel like if I'm gonna do this assignment, there could be errors and like can you still pass in if you just create a code, but then there are errors along the way? Like
You
I
can pass as long as you do the basic code, you can pass. But it's very I look, for example, if you go back and watch the recording session and just follow step by step, then uh, at least you would have a basic version of that. There could be errors, uh, but you you should have a working version of that, don't you?
okay. And like I was looking at decision trees, right? And then there's different types as well. So on the assignment thing, it says you can use ID3. That's different to like cart, right? Because yeah, so we can use that too as an option. Is that
Yeah.
correct?
Yeah. I think the only difference of there is the way you code up this measurement. If you use a different way of measuring,
Yeah.
then you have a different type of tree.
Okay. Because the other one I think focuses on Gini index or something.
Yeah, you can. Yeah.
Okay. And
Maybe probably if you are not very good at coding, the perception one is easier to code.
is it?
Also, later I will introduce the implementation uh, neural networks. Neural networks, although the name carries, you think that it's a loaded notion, um, but it's a really convenient to code up a neural network model. It's the coding part, the hands-on coding part is less than decision trees. Decision trees is probably one of the more difficult code models to code up.
Oh, okay.
Yeah.
And what about like data sets? Because like it says, do we just use one? Can we just use one type, or do we need like two?
You can just use one type. We do not have too much requirement on that part. We because the rationale behind that is apply machine learning methods to practical problems has a much wider and different focus than what we can do at the fundamental level. So we decide that maybe at this stage, it's better to let students understand how machine learning works and what is the basic principle of well this technique. For this reason, we do not have much requirement on how practical or complex the data set you will be using in complete doing assignments.
Yeah, and if I was to choose like perceptron, because you said it might be easier than the decision tree, can you use like can the iris data set be used on that, or you need another type?
Yeah, you can. Yeah.
That one? Okay.
Yeah.
All right.
Yeah.
And like I just went and looked, like I just typed iris data set and you can find it on Kaggle or something like that, right? Is it the same?
I believe that our data set is extremely easy to combine.
Is it?
Yeah. Then you are done. It's just as simple as this.
Oh, okay. So I just type that, and that the data set can be found like.
Yeah,
Oh, okay. So if I like,
really hands-on.
oh, it's already on there. So is it the same? Like, is it the same data?
It is what we have always been using. It's here.
Yeah.
It's
Okay.
here.
Because like in the beginning when I was trying to like when I was testing putting data on the Google Colab, like I was actually having a bit of trouble because I wasn't really familiar. Like it was like, yeah, okay. So all I do is just type those codes in, and the Iris one will just pop up like that.
Yeah, that's the reason I typed my apps, because we are using the same apps. We already have an X
Okay.
app there. You can use X and Y there, and then you can play with X and Y, and you get well, your hands dirty, get much better understanding. Things will get much smoother.
Okay. What's yeah, I remember sound really silly, but what's my_X? Or you just named it like that?
Yeah,
X.
yeah, you can just name it anyway.
Okay. All right. Yeah.
Yeah.
All right. I think that's enough for my questions for now. Yeah.
Okay.
June, there was one more addition to the question, that let us consider that we also check generalization, because let's say if what we teach is our perceptron just works on iris dataset with 2 attributes, because we hard code the number of weights, and then we also don't limit the maximum iterations. So these sort of modifications take you to the full mark point in the program.
Okay. Yes. We have yeah. Please be noted that, because yes, I didn't mention that, because we will have a dedicated discussion about training and test in right into next week. Yes. Well, please be noted that here you have the full X. If you type maybe my, you will find there are 4 attributes here and 155 samples. And in the example I used before, we have simple. Even if let me, if we have simple, yes, we only have simple. Simple X. Okay, I take 100 of that. However, this 100 belongs to the first 2 classes, and this belongs to 3 classes. This number difference is here. And there is another difference, which is more important. You see, these 100 samples have been split into 2 groups. We only use the training group to run the algorithm, and there is another group which is validation. That is what have been introduced in the previous subject, the introduction to data analytics, and that's a very important. This is a very important step whenever we want to do any machine learning stuff. We will discuss this in the next lecture. For now, there is a very simple way to construct your data in such a way. You can see you have a specific functionality from the scikit-learn model selection module. There is a function called the train test split. Well, please read the help document there. Maybe I can just type. So basically, if you provide the train test split, a set of samples and a set of labels, and tell it to, okay, please allocate maybe 1/3 for test only. When training, I'm not using that, and we'll return a shuffled set of training and the test subset of the data samples, which is really convenient. Um, when when practice our assignment, please follow this simple guideline. It's just a way of understanding things. When it comes to coding, it just takes you a very few extra effort. Okay, thank you. I have received a happy hump day. What is a hump day? Okay. Well, if no more questions, maybe we can finish here.
I think Ki Mong has some question.
Yeah, sorry, I have
Please.
one more question. So may I ask, can I use pandas in our assignment too?
Yeah, you can. And I think that is what we have used in the demonstration code here. This is embarrassing.
Yeah, because I saw most of the demo code are NumPy or NumPy, one like that. Yeah, but
Get here. Yeah, look,
okay, cool.
I used the pandas to process the data.
All right, cool. Thank you very much.
Please be noted that the pandas and the NumPy works in a very similar way. However, they have some very small differences that could give you trouble if you do not pay attention. But this is really minor issues.
Okay, thank you.
Okay, sure. Yeah, let's ramp up. And thank you very much for being with us. See you next week. Bye-bye.